Welcome back to the deep dive. Our mission here is always the same. Take a mountain of dense technical requirements, stack it against real-world performance data, and distill it down to the absolute nuggets of actionable knowledge you need to win.
Exactly.
Today, we are strapping ourselves into the world of Formula Student Electric. And this isn't just about designing a fast car.
Not at all.
It's about surviving the rule book and maybe more importantly, actually finishing the endurance event.
And that second part, finishing, that is the strategic core of this entire deep dive. What we're doing here is guiding a new team, helping them establish a truly world-class electric powertrain architecture in their very first year.
Okay.
Our mission is to fundamentally transform how you think about functional safety. It just cannot be seen as some dreaded compliance checklist you have to take off.
It has to be more than that.
It has to be viewed as a strategic competitive advantage.
That shift in mindset from, a compliance burden to a performance enabler, that seems absolutely necessary when you look at the raw data.
It's critical.
You've noted that based on, 2 decades of analysis from all the major Formula Student series globally, FSG, FSAE, the Asian series,
That's right.
somewhere between 35 and 40% of electric vehicle teams fail to finish the dynamic events.
It's a shocking number, isn't it?
And it's not because their motors blew up. It's because of electrical inspection failures or, and this has to be even more frustrating, what you call false positive shutdowns right on the track.
Exactly.
Yeah.
I mean, can you imagine? You design a car that, on paper, should absolutely sweep the competition, only to have a momentary noise spike trick your insulation monitoring device, the IMD, into thinking there's a ground fault.
Yeah.
And poof,
System shutdown. Race over.
0 points.
Yeah.
Performance without reliability is just potential energy. It's useless.
So how do we fix that? What's the approach?
We approach this with structured strategic thinking. We apply that top-tier system engineering methodology, the V model, to develop a really robust engineering requirement specification, an SOR.
And this SRR provides the blueprint for that first year. What are the key areas it's going to tackle for us?
We've segmented the requirements into 5 core technical subsystems, and we move sequentially down that V model.
Okay.
So we start with signal integrity, then thermal management, compliance, control logic, and finally EMC. The overarching goal is to achieve such extreme fault tolerance and determinism that you can safely push the thermal and electrical limits of the vehicle.
Knowing the system will accurately differentiate between, just noise and a genuine catastrophe.
That's the holy grail.
Okay, let's unpack this core philosophy first. We're talking about safety architecture. What is the fundamental difference in safety philosophy between, say, a mass-produced commercial EV designed to last 15 years and a Formula Student car built for just instantaneous peak performance?
The difference is defined by risk tolerance, life cycle, and the necessary response time. Commercial vehicles, they operate in an environment where fault rates are managed over decades, so they prioritize what we call fail operational capability.
Meaning, if a minor sensor fails, the car can still get you home.
Exactly. It enters a limited operating mode, a limp home mode, rather than just shutting down completely on the highway. FSE safety, on the other hand, is it's binary and immediate.
Binary and immediate. What does that mean in practice?
It means the rules dictate that once a critical fault is detected, and we're talking high-risk events like overvoltage, a severe insulation failure, or an unintended acceleration, the system doesn't try to limp home.
It just stops.
It must force a safe state. And that means physically cutting the high-voltage power loop, and it has to execute this action within an incredibly tight time window,
How tight are we talking?
typically less than 500 milliseconds.
Wow, that 500 millisecond response time is almost instantaneous in human terms. So, what if the main vehicle control unit, the VCU, freezes? A software crash. How can you guarantee that cutoff still happens?
That guarantee is achieved through the shutdown circuit, the SDC. You have to think of this as the central nervous system, and it's designed to operate completely independently of the VCU's main processing logic.
So it's a hardwired system.
It's a low-voltage, hardwired series circuit. Think of it like a physical chain. Every single critical safety device, your BMS, the IMD, the brake plausibility device, emergency buttons, the inertia switch, every one of them forms a critical link in that chain.
And mechanically, how does breaking that chain translate into cutting the main power?
So the chain physically controls the coils of the accumulator isolation relays, the AIRs. These relays are the final physical gatekeepers of the high-voltage system.
And they're fail-safe by design.
They are. If you remove power from their coil, a spring forces them open, physically isolating the battery pack. So if any safety device in that SDC chain detects a fault, it instantly opens its contact.
Your chain break.
The chain breaks, the error coils are de-energized, and the high voltage is physically, mechanically cut off from the motor and inverter. And the most important thing to realize is that if the SDC is broken, it doesn't matter what your VCU is trying to do. The power is gone.
So for a new team trying to implement complex redundancy, that fail operational approach, it sounds like an engineering nightmare.
Oh, the risks are exponential. The strategic design philosophy for a startup team absolutely has to be fail-safe.
Why? What's the risk with trying to be more complex?
Well, when you introduce fail operational redundancy, say multiple parallel power loops or complex arbitration logic, you multiply the required software complexity by an order of magnitude. And student teams often struggle most with debugging complex software.
Interprocess communication failures and that sort of thing.
Exactly. If your logic tries to decide which component to shut down, or if it should shut down, you introduce non-deterministic risk. Failsafe is beautifully simple. If the threshold is crossed, the car stops. End of story.
And that simplicity frees up engineering resources to focus on making the 100% power mode robust, rather than spending 80% of their time debugging some 50% limp home mode.
That's it. You focus on what wins races.
So to achieve that reliable fail-safe system, you rely on two core engineering principles. Let's start with the one that prioritizes physical components over lines of code.
That is the hardware priority principle. And this is a non-negotiable tenet derived directly from ISO 26262 thinking.
Okay.
Critical safety functions, specifically those that protect against catastrophic failure like unintended acceleration or ensuring a fault gets latched, they cannot and must not rely on programmable logic. They must be implemented in non-programmable, dedicated analog or fixed logic circuitry.
Why is software inherently more risky than, say, a 555 timer chip or a simple comparator?
Because hardware fails predictably. If a resistor burns out, its value changes, and the circuit stops working in a specific, measurable way.
Okay, I see.
Software, especially under racing conditions, fails in these frustrating, non-deterministic ways. Imagine a race where the VCU's been running for 20 minutes under heavy thermal load and vibration, a poorly written interrupt handler, or a memory leak.
From a forbidden dynamic memory allocation, for example.
Exactly. That can cause stack overflow or memory fragmentation.
Yeah.
The processor suddenly crashes, the system hangs, and often fails to execute that crucial safety instruction to open the SDC.
So if your BSPD relies on that VCU to read the brake sensor and then run the CUN, you're exposed.
You've introduced an unacceptable risk. By contrast, a hardware-based BSPD, using simple analog comparators, is completely immune to software crashes.
That's a profound distinction. Hardware fails deterministically. Software fails in confusing ways. What's the second principle regarding power independence?
The second is electrical isolation. You must have strict galvanic isolation between the high-voltage system, the proportion side, and the low-voltage system, which is the control and safety side. This is fundamental.
And the SDC itself.
Even more critically, the SDC itself has to be independently LV supplied, often directly from the low-voltage accumulator. This ensures that the safety logic remains fully active and capable of cutting the ARs even if the main HV bus fails catastrophically.
So even if the battery pack shorts out and the HV power collapses, the safety system is still alive and ready to act.
It has to be. The safety system must be powered and ready to intervene, even if the primary power source it's protecting has already failed.
We're clearly targeting the absolute highest safety standards here. You mentioned using the formal automotive safety integrity level, or ASIL framework, to guide this process. How does a team use the HACARE process, the hazard analysis and risk assessment, to get specific ASIL ratings for components like the BMS?
The HACARE process is really just a structured way to quantify risk. You look at 3 factors for every potential hazard, like unintended vehicle motion or uncontrolled battery thermal runaway.
Right.
You assess the severity S of the potential injury, where S3 is life-threatening. Then the exposure E of the driver to that hazard, E4 being high probability. And finally, controllability, see the driver's ability to prevent the hazard through immediate reaction. C3 means it's difficult or impossible to control.
And what level does that yield for our most critical systems?
For those critical hazards like BMS monitoring, which prevents explosion via overvoltage, and unintended acceleration prevention, the combination of high severity S3, high exposure in a race, E4, and low controllability, C3, leads you inexorably to the highest required safety integrity level, ASIL.
So ASIL-D. That means we aren't just following rules here. We're aiming for a systematic elimination of risk through some highly rigorous design and process controls.
Precisely. Everything we're about to discuss, the filtration, the redundancy, the testing, it's all mandatory because we are targeting ASIL-D performance on those critical functions.
Okay, let's dive into the nervous system then, focusing on that insidious problem of noise. This is where it gets really interesting, because the car's electrical environment isn't passive.
Oh, not at all. It's violently aggressive.
The inverter, using pulse width modulation, is constantly generating these huge high-frequency voltage spikes. How exactly does that high DVDT, that intense rate of voltage, compromise the most critical safety sensors, particularly the insulation monitoring device?
It's pure electromagnetics.
Mhm.
When the inverter switches between phase poles, which it does, 8 to 20,000 times per second, you create intensely rapid voltage changes, high DVDT.
And that noise has to go somewhere.
Right. Due to parasitic capacitance, the inherent capacity between the high voltage conductors and the chassis ground, and between the HV wires and adjacent LV signal wires, that noise couples. It's like throwing a high-frequency current spike directly onto your sensitive data line.
And the consequence of that is?
The common consequence.
Okay.
The IMD signal, which is extremely sensitive, gets corrupted. This leads to false positive ground fault reports, or the VCU failing to decode the status correctly, which, according to our fail-safe philosophy, means an unwarranted, race-ending shutdown.
So the VCU sees a clean signal, but the noise riding on top makes it believe the car is unsafe. Let's focus on the standard IMD, the Bender IR1553204. Its output signal is our target for cleaning up.
And the IMD is smart about this. While the inverter is operating up in the kHz range, the IMD communicates its status via a very slow, specific PWM signal, typically between 10 Hz and 50 Hz.
So they're in completely different frequency spectrums.
And that spectral separation is our greatest advantage. The VCU's job is precise. Measure the frequency to determine if the device is healthy or faulted, and the duty cycle to determine the actual insulation value. If we see 40 Hz for device error or 50 Hz for ground fault, SDC cutoff is mandatory.
Our task then is to ensure that 20 kilohertz noise doesn't look like a 40 Hz signal.
Exactly.
To exploit that frequency gap, we need a filter that's almost surgical. You specified an RC low-pass hardware filter. Can you elaborate on the design constraints for this?
This filter is absolutely mandatory. It must be a passive component physically installed right at the VCU input connector. The objective is to establish a cutoff frequency, ideally around 100 Hz to 200 Hz. Let's aim for 150 Hz.
And why 150 Hz specifically?
Because it's far above the IMD's maximum communication frequency of 50 Hz, but it's radically low compared to the inverter noise, which starts at 8 kHz. This steep roll-off ensures the high-frequency noise is attenuated by many, many decades, while our critical 1050 Hz signal passes through virtually untouched. It's your first and most critical line of defense.
And the components themselves matter immensely here, right? Especially given the harsh physical environment of a race car. You pointed specifically to the capacitor material.
Component choice is what separates a robust design from a fragile one. You must specify 100 NF capacitors using C0GNP0 ceramic material.
Now, why does that matter so much?
Standard ceramic capacitors suffer from two huge issues in a racing environment. First, temperature drift. Their capacitance changes as the temperature rises, which shifts your carefully calculated cutoff frequency. C0G provides superior temperature stability.
And the second issue?
Second is critical. Standard ceramics exhibit the microphonic effect.
Wait, the microphonic effect, what does that mean in practical terms inside the race car?
Think about what a capacitor is. It's using ceramic material as a dielectric. This material is piezoelectric. Now, in a Formula Student car, you have intense chassis vibration. When a standard ceramic capacitor vibrates, those physical vibrations are converted into tiny, measurable voltage changes. It literally acts like a microphone picking up chassis noise. This vibration-induced voltage modulates your clean IMD signal, corrupting the filter output and potentially triggering a false shutdown.
So using C0G material eliminates that piezoelectric response, ensuring the filter stays stable regardless of vibration or heat.
That's the key.
That's a huge aha moment. You're designing out a failure mode that is completely invisible until the car hits a curb.
Okay, moving on to wiring discipline. We need to address the open collector output of the IMD. I know so many teams fail scrutineering just because they get this one simple wiring step wrong.
They absolutely do. The IR1553204 is a high-side switch. It can pull the signal line up to its positive supply, but it is incapable of pulling the line down to 0 volts on its own.
It's an open collector output? It is. which means it requires an external component, a $2 2-tex omega pull-down resistor connected between the signal line and the GLV, the ground low voltage. Without that resistor, when the IMD tries to switch the signal off, the line just floats, picking up ambient noise and producing erratic readings. It's a guaranteed scrutineering failure.
So the pull-down resistor is necessary for basic functionality, but does this little component also integrate into our fail-safe architecture?
It does, and this is a beautiful example of elegant, simple hardware redundancy. If the signal wire connecting the IMD to the VCU were to break, say, it chafes through completely,
Okay.
the VCU input line would immediately lose its connection to the IMD. But because of that pull-down resistor, the VCU input is immediately forced to ground potential. It reads a solid 0V.
And your software is mandated to see that as a fault?
Our VCU software is explicitly mandated to interpret a continuous 0V, which corresponds to 0 Hz, as a total signal loss and thus a critical fault. This forces a shutdown within 100 milliseconds. That simple resistor acts as a critical safety mechanism against broken wires.
Excellent. Now let's tackle the complexity of the CAN bus. The battery management system, the BMS, lives inside the battery container, which is fundamentally referenced to the high voltage negative. The VCU is outside, referenced to chassis ground. We have a fundamental isolation conflict.
That is the core of the problem. If you directly connect the BMS CAN transceiver, which sits at HV potential, to the VCU CAN transceiver, which sits at GLV potential, you are effectively bridging the isolation barrier.
You're creating a conductive path.
You're creating a path for high-frequency noise and destroying your isolation rating. It's a severe safety breach.
So galvanic isolation is non-negotiable for any signal crossing that high voltage barrier. What does that implementation actually look like?
It means all CAN communication entering or exiting the accumulator container has to pass through a galvanic isolator. We'd recommend using robust integrated isolators, something like the TI ISO 2042 or the analog device's ADM 3FE3.
And these chips use what, miniature transformers or capacitors?
Exactly. They transfer the data signal magnetically or capacitively across a physical barrier without any direct conductive link.
And what are the safety ratings required for that barrier?
The barrier has to be rated to withstand continuous high voltage, at least 1000 VDC continuous, but critically, it has to withstand a peak transient voltage of 2500 V or more.
Where does that kind of peak come from?
When the AR is open, they're switching off inductive loads, like the inverter capacitors and motors. This rapid current cut generates massive back EMF spikes. The isolation barrier has to be robust enough to just shrug off those 2500 V spikes without failing,
Otherwise, the surge jumps the barrier and potentially fries the VCU.
leading to an uncontrolled state. And on top of that, the power supply for the high side of these isolated transceivers must be provided by dedicated, isolated DC-DC converters. You can never share any ground across that isolation barrier.
We've established the hardware filter, but you emphasize that it's insufficient on its own. Noise bursts can still corrupt signals momentarily. What's the final line of defense in the VCU software?
The final line is a robust software glitch filter, or a pulse watchdog. The VCU uses input capture interrupts to accurately measure the period of the incoming IMD signal. The key is to avoid these nuisance trips.
Right.
So if the IMD signal, say it's at 10 Hz, momentarily spikes to 45 Hz for one single cycle because of a noise burst, the system has to ignore it.
So you mandate a delay.
The software is mandated to require continuous detection of the abnormality for 3 full cycles before it's allowed to trigger the SDC.
Why 3 cycles? What does that translate to in terms of time?
Well, since the IMD's maximum frequency is 50 Hz, one cycle is 20 milliseconds. 3 cycles gives you a fault detection window of about 60 to 300 milliseconds, depending on the frequency. It's wide enough to reliably discriminate between a transient noise event and a genuine, sustained ground fault.
But there's an exception, isn't there?
One critical exception: total signal loss. That 0 Hz reading from the pull-down resistor, that specific failure mode, has to trigger a hard shutdown much faster within 100 meters because it indicates a complete wire severance or IMD power failure, which is an immediate catastrophic loss of safety monitoring.
That brings us from the sensitive world of electromagnetic noise to the kinetic, destructive world of heat. The battery pack is the essential power core, but it's also the single biggest catastrophic hazard on the car. How do we extract maximum performance without triggering thermal runaway, which means instant system failure at that 60 degrees Celsius hard limit?
The strategic goal here is to redefine functional safety as a performance enabler. If we just wait until the cell hits 59.9 degrees and then shut down, we failed. Passive shutdown at 60 degrees means you lose the race.
And thermal runaway is this self-sustaining reaction.
It is a self-sustaining exothermic reaction. The internal separator melts, causing internal shorting, which generates more heat, which causes more melting. It's rapid and incredibly destructive. Our strategy has to be proactive derating.
Meaning you remove the heat source, the current well, before you ever approach that hard limit.
Long before.
Let me challenge you on the sensor requirements. The rules often mandate monitoring only 30% of parallel cell groups. You're requiring 100%. Isn't that hugely complex and expensive for a first-year team?
It is more complex and it's slightly more expensive, but the trade-off is 0 points versus points scored. The assumption that 30% coverage is sufficient relies on perfectly uniform manufacturing and cooling, which just does not exist in the real world.
So hotspots can appear anywhere.
They occur randomly, due to subtle internal resistance differences between cells, or more commonly, cooling dead zones that your CFD might miss in the real-world assembly. Missing one hotspot cell that reaches 60 degrees results in a full AMS hard cut, 0 points, and a massive safety incident. Monitoring 100% of groups is a fundamental investment in reliability.
Where exactly should those NTC thermistors be placed to get the most accurate critical reading?
Placement is crucial. You have to target the primary heat conduction path. That is typically the cell's negative terminal tab or the nearest bus bar connection.
So you get the fastest indication of the core temperature.
Exactly. The heat's generated in the core and conducted out through the terminals. Placing sensors indirectly, say on the outside of the plastic casing, introduces significant latency and unreliability.
Yeah.
We can't tolerate that.
Now for the control strategy. In dynamic systems, engineers love to use PID controllers, proportional integral derivative. Why do you recommend strictly avoiding PID for thermal derating in this specific application?
PID controllers are fantastic for systems with stable inputs, but a battery pack has massive thermal inertia. The heat energy stored in the cell structure takes time to dissipate. If you try to aggressively use the integral term of a PID controller to drive the temperature down,
The system builds up momentum.
that's it. The integral component builds up momentum. We call this integral windup.
Can you give us an analogy for that?
Imagine you're driving a very heavy truck and you're trying to brake precisely at a stop sign. If you wait too long to apply the brakes, that integral term, the accumulated error, makes the PID overcorrect, forcing a hard brake.
Okay.
In the thermal system, this overcorrection, trying to maintain a precise temperature near the limit, causes the temperature to briefly spike past 60 degrees due to that thermal momentum, even if your average temperature is lower. And that momentary spike
Triggers the hard cut.
triggers the AMS hard cut. A PID risks failure by being too reactive.
So instead of a reactive controller, you favor a preventative, simple, and deterministic approach, the lookup table strategy.
Exactly. We use a deterministic linear mapping, lookup table.
Yeah.
It's predictable, and it removes the power source gradually. The strategy is non-negotiable and based on the highest single temperature reading from all those cells.
So what does that map look like?
Below 45 degrees Celsius, that's your optimal performance zone. You get 100% maximum current. Between 45 and 58 degrees, that's the performance derating zone. Here, the VCU linearly decreases the available current limit, moving from 100% down to 0. This gently removes the heat source.
So it gives the cell time to recover?
It does. And then, at 59 degrees, we have a software buffer. The software forces an immediate 0 Newton-meter torque output. It's a final, rapid software intervention.
And 60 degrees is the immutable hardline.
That's it. AMS triggers the SDC. This deterministic mapping ensures the driver feels the performance reduction well in advance of the hard limit. It gives you control over your DNF risk.
Beyond the electronics and software, we have to address the absolute worst-case scenario, a thermal event causing cell propagation. How do we use mechanical design to buy the driver critical evacuation time?
This is mechanical functional safety. If one cell goes into thermal runaway, our primary goal is to interrupt the conduction of heat to adjacent cells. So we mandate the use of 6 millimeter thick flame-retardant barriers.
What kind of materials are we talking about?
Things like mica or high-performance aerogel placed between the cell groups. These barriers don't stop the runaway in the first cell, but they dramatically delay the thermal propagation rate. Every second you gain is critical time for the driver to get out.
And the accumulator container itself needs to manage the massive explosive pressure generated during a venting event.
Precisely. When a cell vents, it releases hot, flammable gases and plasma. The accumulator container has to include explosion vents or rupture discs designed to fail predictably.
And the key here is directionality.
Directionality is everything. These vents have to direct those high-temperature gases and flames away from the driver's cockpit, typically rearwards, and toward the outside of the vehicle. If you fail to manage that path, you've turned the battery container into a directional weapon aimed right at the driver.
And just a final word on the control of the active cooling system, the fans and pumps.
The control logic has to be fail-safe and deterministic. Cooling fans and pumps must be controlled based solely on the highest single-cell temperature, not the average. If one cell is hot, the whole system has to cool.
And you verify this with CFD.
Computational fluid dynamics simulation is mandatory. You have to prove that your airflow or coolant path is uniform and that you've eliminated all stagnant air zones that could lead to localized overheating. If your model can't prove uniform thermal extraction, your design is flawed.
Yeah.
We shift gears now to the practical, sometimes painful reality of scrutineering and environmental robustness. We so often see teams with championship-level technology fail because they overlook these small, physical details of compliance.
Especially the rain test.
Especially the rain test.
Call it the garden hose paradox. You design this marvel of engineering for 200 kilometers per hour, but it fails because it can't handle a simple water spray test. What stands out to you as the most frequent and most embarrassing failure mode for teams during that test?
It is almost invariably moisture infiltration. Water finds the path of least resistance.
Cable pathways, bad seals.
And critically, unused connector cavities. This infiltration reduces the insulation resistance, the RISO, between the HEV bus and the chassis ground. And once that resistance drops below the required 500 ohms per volt, the IMD detects a genuine ground fault, and you're done.
Let's start with the connectors then. What's the standard and what's the specific discipline required to ensure their integrity?
The standard requires all connectors exposed to the environment to meet stringent ingress protection ratings. At least IP67, which is dust-tight and temporary immersion, but ideally IP69K, which handles high-pressure, high-temperature washdown.
And you'd recommend specific models?
For a new team, absolutely. Stick with the proven ones.
Yep.
Deutsch DT or DTM series for low voltage, and something like an Amphenol PL or TE HVA 280 for high voltage.
And the critical detail you mentioned, the blind plugs. Why are these so often forgotten? Why are they so necessary?
Teams buy an 18-pin connector, but only use 12 pins. They think the primary rubber seal around the cable bundle is sufficient. It is not. The internal cavities for the 6 unused pins are often open to the exterior.
So water just bypasses the main seal.
It bypasses the overall environmental seal, travels down those empty cavities, and can reach the internal contacts, causing shorts or just wicking moisture through capillary action.
Yeah.
Every single unused cavity in any multi-pin connector must be filled with a dedicated, purpose-built sealing plug. It's literally a 50-cent part that saves your $50,000 car from failure.
That detail is invaluable. Moving to the points where cables enter the sealed enclosures, the cable glands, what discipline is required there to maintain both sealing and EMC integrity?
You need 2 things from the glands, a perfect seal and a perfect ground termination. So you must use EMC-grade metallic cable glands like the lap skin top MSSCM.
And why are those essential?
Because they include metal spring fingers that clamp down on the shield braiding of the cable, ensuring a 360-degree shielding braid ground. This is absolutely crucial for maintaining EMC integrity.
And what about the physical installation rule for these glands?
The installation rule is about preventing stress on the seal. After the cable exits the gland, it has to maintain a straight path for at least 5 times its diameter before the first bend.
And if you bend it right away,
You exert uneven side-loading pressure on the internal sealing ring. You create a tiny gap, and that's all water needs to get in. Following the 5 times diameter rule ensures even, uniform compression of the seal. It guarantees the IP rating.
you mentioned a paradox earlier. The battery box has to be sealed for waterproofing, but it also has to breathe. That sounds contradictory. Why does a sealed box need to breathe?
It's a physical necessity driven by thermodynamics. When the battery box is running, it heats up, the air inside expands. When the car stops or the cooling system engages, the air inside cools rapidly and contracts,
Creating a vacuum.
creating negative internal pressure. If the box is perfectly sealed, that negative pressure acts like a powerful vacuum, actively sucking ambient air and any moisture vapor past gaskets and seals into the enclosure. Over time, this ruins your insulation resistance.
So the solution needs to equalize the pressure without letting water in.
Precisely. You have to install specialized Gore-Tex breather vents, which use an EPTFE membrane. This membrane has pores large enough to allow gas molecules, air, to pass freely instantly balancing the pressure.
But the pores are small enough to block liquid water.
They use surface tension to block water, maintaining the IP67 rating. But a word of caution, you have to install these vents in shielded areas of the box, protected from direct high-pressure water spray during the rain test.
Finally, let's talk chassis ground. Ground continuity seems basic, but it's a frequent failure in scrutineering. What's the standard measurement and where do teams fail in execution?
The ground continuity check is critical for both safety and EMC. The rule requires that the resistance between any conductive vehicle component, the chassis, suspension, a radiator, and the GLV reference point must be extremely low.
How low are we talking?
Typically less than 300 milliamps, and in some series it's even less than 100 milliamps.
How does that resistance measurement spike so easily?
The most common failure is ignoring surface treatment. If you use anodized aluminum for your chassis or mounting brackets, you have to remember that anodization is an insulator. It's a layer of aluminum oxide.
You have to remove it.
You must mechanically remove that anodization sanding, scraping at every single grounding point before you attach a lug or a bolt. If you bolt a ground strap onto an anodized surface, your resistance will be infinite.
And for carbon fiber.
For teams using carbon fiber structures, which are inherently non-conductive, you have to integrate specialized grounding solutions, like embedded copper mesh, or using conductive washers connected directly to the chassis GLV reference via robust grounding braids. A perfect chassis ground is fundamental.
So we move to control logic and the most frightening safety event, unintended acceleration. We need to prevent the classic runaway scenario. Since the rules explicitly forbid relying on the VCU's software for this critical safety decision, it means the brake system plausibility device, the BSPD, must operate as a fully independent, non-programmable hardware failsafe.
That is the core ASIL-D requirement for preventing unintended motion. If a software bug or a shorted wire or a failed sensor pins the accelerator pedal signal to maximum, the car must stop the motor, even if the driver is simultaneously applying maximum braking.
And the BSPD is the key. You call its architecture a masterpiece of analog reliability over digital complexity.
It really is.
Let's detail that required architecture. How do you construct that critical, timed, decision, logic detecting, simultaneous brake, and power using only analog and fixed logic hardware?
Okay, so it has to be a standalone PCB or module. No general-purpose microcontroller or FPGA that could run errant code. The logic chain is precise and deliberate.
So where do we start? The inputs.
First, the inputs. You need two comparators, typically using a robust chip like an LM393. Input 1 is brake. The comparator detects the analog voltage from the brake pressure sensor. If the pressure exceeds the hard brake threshold, usually 30 bar, the comparator outputs a clean HEH signal.
Indicating the driver is standing on the pedal.
Exactly. Input 2 is power. A second comparator monitors the current sensor output. If the motor power output is greater than 5 kilowatts, a high sustained power output, this comparator also outputs HIGH.
So we have two high GH signals simultaneously present. We'd use a simple A and D gate to detect that conflict. But that brings us back to the nuisance tripping issue, a rapid but legitimate brake and throttle overlap during a dynamic driving maneuver.
And that is the crucial design problem that separates good engineering from bad. If we shut down every time the driver touches both pedals for 100 milliseconds, the system is unusable.
So you need a delay.
You must incorporate the timing circuit. This is the fourth element. You use an RC delay network or, more reliably, a dedicated timer IC, like the 555 timer chip configured in monostable mode. This circuit guarantees that the A&D gate's output must persist for a continuous period of more than 500 milliseconds before it's allowed to trigger the final safety action.
And that window is wide enough to ignore the quick heel-toe stuff but catch a real runaway.
It aligns with human reaction time and ensures we only act on sustained, genuinely unintended acceleration.
And once that 500 millisecond threshold is unequivocally passed, the fault has to be permanent and require a physical reset.
Correct. That's the fifth element, latching. Once the timer times out, the fault must be latched. This is usually done with a silicon-controlled rectifier, an SCR, or an SR latch. Once that SCR fires, the current path is established and it remains locked in that fault state.
And the only way to clear it is to power cycle the whole LV system.
A physical, deliberate power cycle of the main switch. It requires intervention from the driver or the pit crew. This fulfills that fail-safe requirement. A critical fault requires a conscious decision to re-enable the system. The latched output then drives a relay to physically break the SDC loop.
That detailed hardware circuit is the final defense. But parallel to this, the VCU is running its own software checks, a torque plausibility check, or TPC, which acts as a smoother, earlier warning system.
The TPC is the first responder. The VCU is constantly running parallel software checks. If the brake pressure exceeds its threshold and the accelerator pedal position sensor, the APPS, is simultaneously reporting an input greater than 25%, the VCU has to immediately zero the motor torque command within 500 meters.
It's a faster, less disruptive cut, but it's not the final safety authority.
It is not.
And what about the reliability of the APPS itself? What prevents a faulty sensor from just reporting 100% throttle all the time?
Mandatory APPS redundancy. The system must use dual independent pedal sensors, and they often have to be designed with inverse outputs for immediate detection of shorts.
So one sensor ramps from 0 to 5 volts and the other from 5 to 0.
Exactly. The VCU continuously monitors both. The rule is strict. If the deviation between the two sensor signals exceeds 10% of the total range, the VCU has to interpret this as an immediate sensor failure and cut the torque to 0. This eliminates the single-point failure risk of the throttle input.
Finally, software quality itself. Since the VCU and BMS code controls so much, it has to be highly deterministic. You mentioned adherence to MIS-RSC standards.
Yes, for safety-critical code, standards like TRIN 2000-2012 are essential, and for a racing environment, two rules are absolutely paramount for achieving predictability.
What are they?
Rule 17.2 prohibits recursion. Why? Recursion can rapidly consume stack space, leading to stack overflow, which causes non-deterministic software crashes, the exact scenario you want to avoid. Secondly, Rule 21.3 prohibits dynamic memory allocation, no malloc or free.
Why is that so critical in a long race?
Over the course of a long endurance race, dynamic allocation causes memory fragmentation. This leads to unpredictable system instability, latency in response, and eventual crashes. You have to use only static compile time memory allocation. And we also enforce rules like Rule 14.4, requiring all if statements to be explicitly Boolean to improve code certainty. We've addressed noise mitigation at the sensor level, but now we have to address the source and path of that noise, electromagnetic compatibility, or EMC. EMI is the invisible killer. It doesn't leave a fault code or a smoke trail, but it can restart your VCU processor, corrupt CAN messages, or shift sensor readings.
And your goal is managing impedance paths to neutralize it. This often comes down to grounding discipline. What is the fundamental trap that turns a perfectly good shield into a noise-generating antenna?
The fundamental trap is the ground loop trap.
Yeah.
Many engineers instinctively try to ground a signal shield at both ends, believing, that redundancy is safer. But because the chassis ground potential is never perfectly uniform, there are small potential differences between the front and back of the car. Grounding both ends creates a complete low-frequency loop, and that loop acts as a large receiving antenna, absorbing ambient magnetic fields and inducing current flow through the shield.
And that couples interference back into the signal wires.
Exactly. We have to manage HV and LV shielding very differently.
Let's start with the HV cables, the thick orange phase lines and DC bus lines. You mandate grounding the shielding braid at both ends. This seems to directly contradict that ground loop warning. Why is this necessary for HV?
For HV cables, the noise we're fighting is primarily common mode noise due to the extremely high frequency switching of the inverter up in the megahertz range. At these frequencies, the shield's job isn't just to block external fields, it's to provide a safe, low-inductance return path for that noise current to get back to its source, the inverter.
So grounding at both ends creates that low-inductance path.
It does. Using those 360-degree EMC glands at the motor and inverter creates a shunt. This allows the high-frequency noise current to flow directly back, bypassing the entire chassis structure and preventing it from radiating across the car.
And the practical detail here is crucial, the strict prohibition on pigtails. Why does a pigtail twisting the shield into a single wire destroy the effectiveness of this termination?
Because of impedance. A twisted pigtail, even if it's only a few centimeters long, introduces extremely high inductance at high frequencies. Inductance is the resistance to changes in current flow.
Okay.
When you're trying to rapidly drain off high-frequency noise in the megahertz range, that high inductance destroys the effect of the shield. Instead of providing a low impedance path back to the source, the pigtail acts as a very effective high impedance radiating antenna. You must use a 360-degree clamp.
Conversely, for sensitive, low-voltage analog sensor lines and CAN bus lines, we go back to the single-ended grounding rule.
Yes. For LV signal shielding, you must use single-ended grounding, usually only at the VCU or the ECU source end. By only grounding it at one point, you prevent those low-frequency ground loop currents from flowing through the sensitive shield. The shield still acts as a Faraday cage, blocking capacitive coupling, but you eliminate the risk of magnetic interference corrupting your signal.
To ensure all our sensors and ECUs have a perfectly stable, noise-free voltage reference, we need a disciplined LV grounding architecture. This brings us to starpoint grounding.
Starpoint grounding is the foundation of a clean LV system. The requirement is to establish a single physical point, a dedicated low-resistance copper busbar or post on the chassis, which serves as the sole common reference point for the entire low-voltage system. No other ground paths should merge anywhere else.
And what about the difference between clean and dirty currents?
This is vital to prevent noise crosstalk. You have to separate dirty ground, high current loads like cooling fans, pumps, relay coils, from clean ground, which is your sensitive sensors, the VCU power, and the IMD reference.
And they all wire back to the start point individually.
Individually, they only merge at that single designated start point.
What?
This prevents the large current loads from causing ground bounce momentary voltage fluctuations on the ground path that would corrupt your sensitive millivolt level sensor references.
Finally, we revisit the conflict involving the insulation monitoring device. Inverters use Y capacitors for EMI filtering, but you mandate limiting the total value of this capacitance. This seems like a direct conflict between filtering noise and maintaining isolation.
It is a classic engineering trade-off. Y caps provide a necessary path for high-frequency noise to return to ground, which is good for EMC. However, they also provide an AC leakage path between the HV bus and the GLV ground.
And the IMD sees that AC leakage.
The IMD is designed to detect true DC insulation resistance, but when the inverter is switching rapidly, the cumulative total Y capacitance across the system causes the IMD to measure a large capacitively coupled AC current, and it incorrectly interprets that as a low insulation value.
So too much Y capacitance leads to the IMD reporting a false ground fault, causing nuisance tripping.
And ruining your race. Teams have to carefully calculate and limit the total system Y cap value to ensure it doesn't mask the true DC resistance measurement.
We've covered the entire requirement specification, from the analog core of the BSPD to the physical sealing of connectors. We have a world-class SOR. Now we shift to validation. An engineering process only concludes when the design is proven, and that requires formal, structured testing. How does a new team prove they met these exacting standards, short of just waiting for the actual race?
They have to adopt the industry standard,
Right.
the Design Verification Plan and Report, or DVP&R. This is a critical management process. It forces the team to move beyond simulation and create objective, repeatable, and measurable physical tests for every single safety requirement. The DVP&R is the signed document that confirms your system works reliably.
Hope is not a design strategy.
Proof is.
Let's detail the necessary matrix of key validation tests that must be executed and documented before the car ever sees the track.
Okay, we define 4 core validation tests that prove the integrity of the architecture. First, proving the thermal management philosophy. T12.2-02 Thermal Propagation Test.
And this is a destructive test.
It is. It requires taking a representative sample battery module and intentionally inducing thermal runaway in a single cell, maybe with a heating element. The pass standard is simple. Fire or intense heat must not propagate to any adjacent cells within the required time window. This validates the material and thickness of those 6mm flame barriers.
Okay, what's next?
Second, environmental integrity. T12.301 Simulated Rain Test. While the tractive system is actively powered, the car is subjected to the full 120 seconds of high-pressure water spray, simulating the scrutineering check. The pass standard. The IMD reading must remain stable and above the critical 500 ohms per volt threshold, and most importantly, the SDC must not break.
This confirms your discipline in connectors, glands, and the breather vents.
Exactly.
And the most important analog circuit, the unintended acceleration prevention system.
That is the T12.401 BSPD test bench. You have to construct a test harness outside the car and feed the standalone BSPD circuit simultaneous simulated analog signals for high brake pressure and high power output.
And what's the pass standard there?
The SDC relay must open and latch permanently only after the critical designed greater than 500 millisecond delay has elapsed. If it trips early, it's a nuisance trip. If it trips late, it's a safety failure. This proves the determinism of that analog timing circuit.
And finally, verifying the galvanic isolation barriers we discussed.
The T12.501 high pot, or dielectric withstand test. This is essential. You apply a high voltage, typically 1,000 volts, between the LV harnesses and the HV bus, the pass standard. The leakage current flowing across that barrier must be less than 1 milliamp. If it's higher, it indicates a breakdown in an isolation barrier somewhere, meaning your system is catastrophically unsafe.
This level of documented testing instantly elevates a team's engineering rigor. To wrap up, looking at this enormous list of requirements, what is the single most important strategic piece of advice for a new team to internalize?
It is the truth that successful Formula student veterans understand. Reliability precedes speed. A reliable car that passes inspection on Monday, survives the rain test on Tuesday, and finishes the full endurance event on Sunday, even if it runs conservatively at 80% power, scores points.
And it builds that foundational institutional knowledge.
It does. A technologically powerful car that fails scrutineering or suffers a false positive shutdown scores 0 points and causes catastrophic morale failure. Functional safety is the gateway to performance. It is not the obstruction.
So if a team is listening to this right now, what are the 3 immediate, actionable items they should execute this afternoon?
First, immediate component procurement. You need to specify and buy the specialized high-quality safety components now. That means the Bender IMD, the specific C0G ceramic capacitors for your filters, the IP67 connectors, and quality double-shielded cables. Don't cheap out and don't wait.
What's number 2?
Second, prioritize analog hardware prototyping. Before you even think about finalizing a PCB, verify the analog parts of your safety system. Get a breadboard, get that 555 timer, and prove that 500 millisecond delay and the SCR latching logic for the BSPD. Analog circuits are hard to get right in simulation. You have to prove them in physical hardware first.
And the third action item?
Use this SOR as your guide to immediately initiate the failure mode and effects analysis, the FMEA process. You cannot design a safe system if you don't know how it can fail. Use this document as your baseline for defining correct operation and systematically identifying every possible single-point failure.
That is an immense depth of engineering rigor required, from selecting the chemical composition of a capacitor to defining a 500 millisecond delay in a purely analog circuit. It demands integration across physics, software, and mechanical design.
Functional safety demands designing resilience into every single layer of the car. And crucially, it requires traceability. Every safety decision you make must be documented in your electrical system form, the ESF, proving you didn't just meet a rule, but that you engineered the solution.
And the biggest risk isn't a lack of power.
The biggest risk in FSE is not a lack of power, but a lack of preparation and robust physical testing. Managing functional safety is the true differentiator between a mere competitor and a championship contender.
A challenging and provocative thought to leave our listener with, especially those leading a new Formula student team. How robust is your system if the main control unit suddenly goes dark? If your vehicle safety relies on code, it's not safe enough. Thank you for walking us through this critical deep dive.
My pleasure.
That's all the time we have for this deep dive. Until next time, keep digging.